I'm going to talk today about some of the work that we've been doing, motivated primarily by our interest in cloud security. You may have heard of this compute cloud thing. It might catch on. And so one of the problems that we wanted to study in this context was the risk of multiple tenants, potentially tenants that distrust one another, and sharing hardware. And this gives rise immediately to a concern that's commonly referred to as side channels. And so I'll tell you about our work in this space. To set the stage a little bit, there are really two kinds of clouds that I want to introduce you to. One is called an infrastructure as a service cloud. The canonical example here is Amazon EC2. There's a virtual machine monitor running on hardware in big data centers. And tenants ship virtual machines to the cloud to run there. And what we're concerned about is tenants who ship virtual machines that are kind of evil, right? They try to extract information from their co-tenants on this hardware. There's another version of this, platform as a service clouds, where the isolation is performed not by a virtual machine monitor, but by a more traditional operating system, typically today using Linux containers. And so here, again, what we're concerned about is a tenant that ships some tasks into this environment in an effort to extract information. Now, in particular, the kind of side channel that this scenario fits well is usually called an access-driven side channel. And what happens here is that the attacker and the victim run together on shared hardware. Again, there's some isolation software, virtual machine monitor, or the operating system that tries to keep them separate and so that one can't steal information from the other. Side channels arise and allow this information leakage to occur between tenants when typically through the use of shared micro-architectural components. And the ones that we're particularly going to leverage today are CPU caches. And it's not that we are alone in leveraging these. These have been leveraged a lot in these kinds of environments for stealing information, leaking information. And so they're very handy in ways that I'll describe to you as a vector for learning things about who you're running with. Now, there's been a lot of work in this space. I want to point out first and foremost, this is not all our own work. Okay, so this involves a number of our works, but also other people's works in leveraging CPU caches or other kinds of microarchitectural components for stealing information. I am going to focus today mostly on our work because I have the slides for it, right, to be completely honest. But I'll also try to stitch other people's work into this timeline so that you understand how this field's been evolving. And it's been evolving very quickly over the last 5 years or so. So that to try to bring you up to speed on where the state of the art is in these kinds of side channel attacks on shared components, on shared platforms like clouds. And to do that, I need to break down the work in a few different dimensions. One of the ways I want to break it down is based on the kind of cache that is being used for stealing information. And the first one I want to focus on is time-shared caches. And what I mean by this is typically per-core caches, like the L1 instruction and data caches, the unified L2 cache. And the reason I call them time-shared caches is because there has to be a context switch between one party using the cache and another party using the cache, because they're caches that are used on a single core. And so this is essentially what happens in this environment is that a victim and an attacker may be they alternate running on the core. And so the attacker gets some hint, some whiff of what the victim was running or what it was doing when the attacker gets its opportunity to run after the victim. And the works I want to summarize briefly in this space are the first three here, going back now about 4 years to when we were doing this initial work that appeared at CCS 2012. And so let me just sort of describe this attack that we demonstrated for a few minutes to set the stage for the rest of the talk. And so again, we're using CPU caches here to extract information from a victim to a tenant on time-shared caches. We were using the L1 instruction cache. And the attack pipeline that we put together to enable an attacker to steal information from a victim in this environment is essentially broken down into 4 phases. Due to time constraints, I'm really not going to have time to go through all 4 of these. I'm just going to focus on the first 2 stages because they do set the stage for some subsequent developments in the field since then. The first stage being cross-VM side-channel probing. The second one is essentially a machine learning technique to classify what you see out of the cache. And then there's a couple of other stages that I'm not going to focus on so much. But let me start with the sort of the first step of this attack, which is a side-channel cache probing mechanism that borrows from some previous work called prime probe attacks. Now, in a prime probe attack, effectively what you have is you have a shared cache. Again, we were working with the L1 instruction cache. And essentially what happens in a prime probe attack is that an attacker comes along and runs, and in doing so fills up the cache. It reads in a bunch of data, and it fills up the cache with its own data. The way I'm going to refer to this cache is that each column in this sort of now red grid is a cache set. We're looking at what would be a 4-way cache. There are 4 lines in each cache set. And so the attacker primes the cache by filling it up, and then relinquishes the core and lets the victim run. As the victim runs, it comes along and evicts certain things of the attackers that the attacker had brought into the cache. And then when the attacker gets to run again, it effectively retrieves the same data that it had retrieved before and times on a per cache set basis how long it takes to do so. So it sort of gets a timing per cache set of how long it took to refill the cache. And in doing so, it also learns roughly how much of that cache set got evicted by the victim. And that turns out to be a source of information leakage. Your initial reaction might be, well, okay, sure, maybe that's a source of some information leakage, but can you really learn anything interesting out of that? And that's what the rest of the pipeline's about, really, is trying to come up with how you use this signal, admittedly very noisy and kind of coarse, to figure out interesting things. One of the first practical challenges that you face when you try to do this kind of attack is that what the attacker would ideally like to do is get back into the core and see what the victim did after, say, just 1 memory access, okay? Unfortunately, on a modern hypervisor like Zen, you're not going to be able to do that. In fact, if you look at the default Zen schedule, the Zen's default scheduling quantum of 30 milliseconds, by the time you get back into the cache, it's going to basically all be evicted, right? Everything has been thrown out. That's a super long time, 30 milliseconds, to wait to get back into that cache. And so one of the things that we wanted to do was first come up with a way to induce very frequent context switching. That is, how could the attacker get back into the cache much faster than waiting for that default scheduling quantum of 30 milliseconds? And admittedly, this involved somewhat of a hack, right? You need to find some way to trick the scheduler to get back into the cache very quickly. And the way we did it, the way we found to be most effective, in terms of the version of Zen we were working with, was to use interprocessor interrupts. And this will be important later for reasons I'll discuss. But the basic idea is that the attacker would be structured as effectively 2 different virtual CPUs, one of which its whole day job was to sit there and lob interprocessor interrupts at the other attacker vCPU to keep waking it up and causing it to run, okay? And essentially that other attacker vCPU is the thing that was doing the prime probe attack on the victim. And again, the IPI vCPU just existed to wake up the other one as fast as it possibly could. So this is sort of one way that you could induce this kind of frequent context switching to get back into the cache. To give you a sense of what this achieved, it reduced this 30 millisecond window down to a few microseconds in terms of getting back into the cache, which was a huge win in terms of the fidelity of the signals that the attacker could get. Certainly still very far from a single memory access, but much better than that 30 millisecond window. Now, just to remind you, what the attacker is now getting is every handful of microseconds, it's getting a vector of timings, 1 per cache set, 1 timing per cache set, of how long it took for the attacker to bring its data back into the cache. This vector we then wanted to classify in terms of what operation was the victim doing when we sort of saw that snapshot, okay? And to do that, we leveraged some pretty basic machine learning stuff, support vector machines, which I'll get to in a second. But to explain why we wanted to do this, I want to give you a potential target that the attacker might be trying to attack. It's just to sort of make this concrete. And the target I want to put in front of you is a modular exponentiation routine. This computes, given arguments c, d, and n, it computes c raised to the d power mod n. Okay? And this is an ingredient in a very large number of public key or asymmetric cryptographic algorithms. If you know RSA, if you know Elgamal, things like this, you'll recognize this immediately as sort of a central algorithm in those computations. This is a very vanilla, what I would call textbook implementation of modular exponentiation. And I'm keeping it simple here because it's a lot easier to convey in a talk like this, the simple version. And what I want to highlight here is the fact that in this routine, what it's doing is it's looping through the bits of the exponent. The exponent you should think of as the secret. And based on the bit of the exponent, it is doing something in this loop. In particular, there's a branch condition in this loop based on what that bit is, so that if the bit is a 0, you get just a square operation followed by a modular reduction. If, however, the bit is 1, you get a square, a modular reduction, then a multiply, and another modular reduction. Okay? And in some sense, if the attacker can follow the victim's execution through each loop iteration, because it can potentially distinguish these two paths, it could then figure out what the exponent is. And in the scenarios that we're going to focus on, the exponent is in fact the secret. So by following the victim's code execution path, the attacker can figure out what the secret is. Now with that in mind, right, what we wanted to do was take those timings those vectors of cache timings, again, one per cache set, and classify, does this represent a square? Does it represent a modular reduction? Does it represent a multiplication? Or does it represent just something else, which is noise that we have to get rid of, okay, and ignore? And so that's kind of what the classifier is trying to do. To do this, what we did is we took a victim that we instrumented to essentially write down exactly what it was doing when the attacker was able to perform a cache timing, a reading of the cache timings, so that we had labeled instances in a machine learning sense that we could use to build a support vector machine using, let's say, identical hardware and an instrumented victim. And then, right, the idea would be we build this model and we deploy it in a real attack on cloud hardware, okay? Now, unfortunately, the results you get from that classifier are not noise-free. And so the other parts of this attack, which I'm going to gloss over here because in the interest of time, have to do a lot with dealing with the noise, right? So this is sort of stage 3, is some other techniques to get rid of that noise. And then the last part, I'll just talk about just for a moment because it's really a fascinating problem. What the attacker ends up getting out of this style of attack after the noise reduction step is what I would call a series of bits, a sequence of bits, maybe with some question marks in it, but in particular not the entire exponent. It gets parts of the exponent somewhere in the exponent that it doesn't know where, okay? And essentially what the attacker has to do is take all these snippets, if you will, of the exponent and stitch them back together to build what is in fact the full exponent, the full secret that the victim has. And this actually turns out to be quite related to a problem in genome reconstruction. I don't know anything about that field. We had to talk to some people and ask them some questions. But anyway, if you're into that genome reconstruction stuff, we had a very similar problem here. It's kind of an interesting analogy to what we were trying to do. In any case, let me just jump to the sort of the end result of how far this got us. So How effective this attack was depended a lot on the style of scheduler, the configuration of the scheduler that you're working with. There's a distinction between what's called a work-conserving scheduler and a non-work-conserving scheduler. The non-work-conserving scheduler will enforce that every VM is limited to its given budget, regardless of whether or not there are resources available on the platform to let it keep running. So in other words, you just can't exceed your budget, even if you would, sort of by not allowing it to exceed its budget, you leave the machine idle. And in particular, in this case, what this means is that IPI vCPU that's lobbing those interprocessor interrupts as fast as it can eventually gets descheduled because it's just using up too many resources. And as a result, this one takes a little while, right? So we had to run 45 hours, right, with a victim next to an attacker. Now, what was the victim doing? The victim was in a loop, essentially doing modular exponentiations. And you might think, well, that's ridiculous. Nothing like that happens in the wild. Well, first of all, let me point out that 98% of the instructions that the victim was executing were not key dependent. And so all of that stuff that we see, we have to filter out. But in addition, it's actually not that unreasonable to think that you could cause a victim to do repeated exponentiations like this. Think of a web server in a cloud that you just connect to over SSL over and over again. So it's actually not that hard, okay, to get maybe in some circumstances a victim to do this. But even so, right, it took about 45 hours, right, running next to the victim to extract enough information to brute force the key or what was left of the key in about 6,600 guesses. Okay, very tractable to do this. What were we attacking? We were attacking an Elgamal decryption key of a pretty crazy size. It was like 4,096 bits, which should be secure more or less until the heat death of the universe, if you're, roughly speaking. And so reducing heat death of the universe to 45 hours isn't too bad, right? You might say. But if the schedule's work conserving and so doesn't preempt that interprocessor interrupt vCPU from doing its thing, it in fact gets reduced by quite a bit more, down to about 6 hours running next to the victim. And again, right, this relatively artificial setup where the victim was doing its operations over and over again. Don't worry too much about that. Again, part of this pipeline is a noise reduction step that gets rid of that 98% of stuff that isn't key dependent. And so yes, it would stretch out a little bit if the victim wasn't doing these operations over and over again, but it wouldn't stretch out that much. Okay, so we're not really that dependent on that kind of a victim. So that's kind of the punchline of this initial step. One of the things I wanted to highlight is that one thing that was critical to getting an attack like this to work was preempting the victim quickly. And so what the field immediately did in response to this attack is say, okay, well, your problem is the scheduler, right? What you should do is you should change the scheduler so that it doesn't allow an attacker to preempt a victim that quickly. And so that's, in fact, right away what happened. This Unix 2014 paper was some work by some others that focused on the scheduler to fix this problem. Another way in which we leveraged that observation was in some subsequent work that we did to try to fix the problem through adding noise into the caches as you run. Okay, and this is something which I'll describe briefly called Duple. Duple is the German word for chaff. We chose the German word for it because we were submitting to a conference in Germany and we thought that would play well. And it got in and, I guess we made the right choice. But yeah, so Duple is a radar countermeasure that was developed by the Luftwaffe in World War II, where basically an aircraft would disperse material, right? Small pieces of material out in its vicinity. And this material was very reflective in the radar images that were picked up. And so it would sort of make a mess of the radar images. And so we wanted to sort of explore whether there was a possible way of leveraging this idea and defending against these kinds of side channel attacks, in particular without the help of the cloud operator. We thought, well, what could you do if you wanted to deploy a VM to the cloud, but the cloud kind of doesn't care about all the side channel nonsense, but you do. You still want to run in the cloud. Can you address this threat in some way? And so that was this attempt. Now, the intuition behind Duple is to leverage, again, the way the scheduling is happening, this alternating on time-shared caches, where the attacker has to sort of preempt the victim, get in there and look around in the cache. The victim gets to run for a little while before it gets preempted. In particular, what the victim would like to do in this scenario is to leverage a portion of its time to clean up after itself, so that when the attacker gets into the cache and looks around, it's getting a very noisy signal as to what was happening as the victim ran. And in truth, it's not that hard to do this. The attacker and the victim have available to themselves the same kinds of interrupts and timers and so forth that they can work with. And so, in some sense, all we're really trying to do is beat the attacker at his own game. What makes this hard is to do it without hurting your own performance very much, because presumably you don't deploy something to the cloud just for the sake of cleaning up after itself. It has a day job, and it's got to get its work done fast. And so now the question is, how do you do that and not leave footprints in the cache that the attacker can go sift through? Not too surprisingly, right, we use the same interprocessor interrupts in this work, as well as some others, right, some HR timers, high-resolution Linux kernel timers, and so forth. I'll explain how we use them in a moment. The idea is, while the victim's running, it does the natural thing. It's going to take a period of its time while it's executing to load irrelevant data into all these caches to try to fill them up. And here we just did it with the L1 instruction and data caches in the L2 cache. You could also do this with something like the branch target buffer, but we didn't in this particular implementation. There's nothing keeping you from doing that as well. Now, in order to make this run reasonably fast, one of the things that we did to try to minimize the performance impact was to limit what you were trying to protect. Oftentimes, there are libraries, like cryptographic libraries, where these secrets are going to be handled. And maybe you just want to protect those, not everything you're doing, say, in your web server. And so to do that, right, if you're going to limit your protection scope, what we decided to do is to allow someone to mark the, say, library code pages as non-executable at page level, or you configure the system this way, and then our system marks them as non-executable at the page level, so that when you enter one of these, say, cryptographic libraries that you're trying to protect, you take a page fault. Okay, and when you do that, you know, okay, I'm now executing sensitive stuff. And as I do that, wow, I got a phone call. Sorry about that. So as you do that, you want to clean up after yourself while you're executing that in that library. So when you take the page fault, what we did is we just started cleaning up periodically for some fixed number of intervals, after which we re-enabled the page protection. If we were done in the library, then great. We would just go on and keep executing. If we weren't done, we would immediately take another page fault. And then again, you start cleaning for another n iterations. To make this perform reasonably well, we had to adjust n dynamically so that we weren't taking too many page faults, things like that. But pretty simple idea. The other way that we tried to make this go a little bit faster was to skip unnecessary cache cleansings. And what I mean by that is that every time you are getting ready to clean up in the cache, if there were a way to tell whether you were being preempted aggressively, as we thought at the time was necessary for these kinds of attacks to happen, that, well, maybe you shouldn't worry about cleaning up. You should just go on and keep doing your day job. And so the idea would be you need to come up with some way to detect how often you were being preempted and what you were running as you were being preempted, to figure out, do some thinking about whether or not you need to worry. And if you need to worry, then sure, clean up. If you don't need to worry, don't worry about it, just keep going. We found, again, another hack, effectively, to do this detection. Turns out there was a timestamp value in a shared info page that got reset every time you were preempted, so you could sort of tweak it and watch it get reset, and you could tell when you were being preempted. And so this way, you could then do sort of this thinking to figure out whether you needed to clean up. Now, this kind of gave rise to running in one of two modes, which we kind of cheekily called battle mode or sentinel mode. The idea would be that you keep sort of a running average of how frequently you're being preempted. If you see a spike in this or you cross some threshold, that indicates that maybe you're under attack. You better start cleaning up after yourself. And so you sort of increase the frequency with which you're checking in battle mode, say every 3 microseconds, right, using these interprocessor interrupts and so forth. If eventually you see yourself not being preempted very much, you fall back into this a little slower preemption frequency mode of every 15 to 20 microseconds. And just sort of keep this running average, checking it every now and then until you see yourself getting attacked, and then you start cleaning up. Not surprisingly, when you see yourself getting attacked, you're spending a lot more of your time cleaning up. And so what that means is that you're effectively translating a information leakage attack into a denial of service on yourself, but we're presuming here that you would rather not leak the data and get less work done. Now, one of the hard parts about a work like this was actually evaluating how effective it was. This turns out to be a very hard thing to do. Here's one example of a kind of evaluation we were able to do, which sort of leverages the attack I showed you first. And what you see on the right side of your screen are 2 confusion matrices. One is without Duple running at all. So in the original attack, effectively this shows the frequency with which a square was called a square by that support vector machine, or a multiply was called a multiply by that support vector machine classifier, or similarly when you could rule out either one of those 2 things. In general, without Duple running, that attack was able to get an accuracy of about 90% in classifying these kinds of operations. And then our noise reduction steps after that I didn't tell you very much about, were able to overcome that remaining 10% error. With Duple running, unfortunately, well, or fortunately for the defender, right, the accuracy of that classifier drops to about 38%. And our noise reduction steps after that just don't work. Now, it could be that there are folks in the room that are smarter than we are that could figure out a way to overcome that remaining noise. What I can tell you is that we don't know how to do it, but that's not a proof that this is secure, right? All this says is that we don't know how to overcome it. And so, maybe here's an opportunity for someone to come and do better than we did. Now, another thing that, of course, we need to be concerned about here is what's the performance impact of something like this. Now, all of these numbers are when you're not under attack, okay? So if you're not under attack, you're just doing this sort of sentinel mode watching. We saw, say, performance of a web server decay by around 4%, or 3.4%, depending on whether you're looking at throughput or latency. We also did some purely computational things. In the first case, in the Apache web server case, we were just protecting the crypto libraries. In this case, we were going to protect everything. These are some benchmarks that are used for checking parallel task performance. It doesn't matter what they are, but basically what we saw was a runtime slowdown of about 7%. Now again, if you're being attacked and so you're actively defending yourself, the decay is much more substantial. But again, we sort of took the perspective that we presumed you didn't want to leak that data, or you prioritized that over getting work done. Now, and so you might think, okay, well, this is great, or maybe you think it's not great. That's fine too. But one thing that you might think that we made some progress in defending against these attacks that we initially came up with. Unfortunately, remember all that was about the time-shared caches, and nobody at the time had really demonstrated attacks on the simultaneously shared caches. And what I mean by that really is the last level cache. These are not per-core caches. These are instead shared across cores. And in particular, there doesn't need to be a context switch between when the victim runs and the attacker runs. They can run side by side, and the attacker can look around in the last level cache as the victim's running along next to it in another core. And so the next sort of stuff I want to tell you about is what the field did to kind of leapfrog these defenses in the time-shared caches case and jump right into the the simultaneously shared caches to show that, in fact, you could leverage those as well. And one of them I'm going to tell you about was a work from now, I guess, 2 years ago that demonstrated these kinds of attacks in the wild on PaaS clouds, platform as a service clouds. In particular, it's probably worth mentioning that we didn't do the first attack I showed you on actual clouds in the wild. And the reason we didn't do that was because the frequency, this interprocessor interrupt thing that we were doing, was sufficiently disruptive to the platform that we thought it was probably unethical to do this on a cloud where people were paying to run their compute jobs on that hardware. That is, it would actually impact their performance. So we did all those attacks in the lab. What I'm going to tell you about here, however, we did a lot of work to see how intrusive these attacks would be on other tasks running in the wild, and they were sufficiently undetectable that we felt comfortable actually doing this in the wild. So I'll tell you about how we do this. Now, the kind of attack that we leverage here is something a little bit different than a prime probe attack. It's called a flush reload attack that goes back now about 4 years. And in this style of cache attack, it leverages shared pages, which is very common in platform as a service clouds. The reason for this is that in past clouds, they're often running on infrastructure as a service clouds, so they're renting their machines as well. And they want to pack as many tenants as possible into one of these VMs. And to do that, they need to share as much as possible, so across these tenants. And so they share a lot of library pages, for example, between their different tenants. In a flush reload attack, what happens is that the attacker task comes along and evicts something, a chunk. I'm going to call it basically when I refer to a chunk, I mean it's a cache line sized and aligned physical piece of memory. Evicts it from the last level cache. Conveniently, there's an instruction to do this called CL flush. It's not protected. And so you just push this thing out of the cache, and then you watch as the victim runs and check whether or not the victim brings it in by subsequently accessing that chunk and seeing how long it takes to access it. Again, you just time how long it takes to get to that chunk. So this turns out to be a very high fidelity side channel that we're going to leverage in kind of a similar way. Here's a very simple example that I'll use to drive how we use this. This is not a cryptographic routine. This is just a very simple program that sets A to 9 and then checks something about it. And if that something is true, then it increments A. So very simple. And let's say for a moment, for the sake of our discussion, that, okay, here's the control flow graph of that little routine. What the attacker would like to detect is whether or not A is being incremented. So it wants to use this style of flush reload attack to decide whether or not A got incremented by the victim. To do that, right, let's assume for the moment that when you compile each of this program, you end up with chunks, again, cache line sized, aligned pieces of physical memory that map onto the different basic blocks in that little control flow graph. And so you end up with something like this in 3 different chunks. And you want to come up with a way to monitor sort of for the increment operation happening. And so the way we abstracted this problem in general was to sort of come up with an abstraction called what we called an attack NFA that describes a recipe by which the attacker would monitor different chunks over time to notice the execution that it wants to follow. Now in this particular case, right on the left we see that very simple control flow graph compiled into chunks. On the right we see the recipe for how the attacker is going to monitor them. And each node in this little attack NFA describes the chunks that should be monitored for a period of time. And if you see, say, chunk 1 accessed through this flush reload style monitoring, you will then move to monitoring chunks 2 and 3, and so forth. What makes this non-deterministic? There are these annotations on the edge of T1 and T2 and T3 and T4. These are times. All that says is that you need to see chunk 1 accessed between times T1 and T2, and if you see that, then you'll move on. If you see it outside that range, then you'll know you've failed. So it's not really strictly an NFA in the way where you normally taught them in our automata classes, but it's still not exactly deterministic. So that's kind of, you write down one of these attack NFAs and you use it to follow along with what the victim's doing. Unfortunately, we don't know how to develop these attack NFAs automatically. We just do them by hand. And I'll show you a more realistic one here in a few minutes. But if you were to use this attack NFA, you would start monitoring chunk 1 using that flush reload trick. If once you saw chunk 1 accessed, you would move on to monitoring chunks 2 and 3. Once you saw one of them access, say, chunk 2, you would move on, keep monitoring chunk 3, and when you see chunk 3 accessed, you know you've finished, and you move on to the state with the double circles that say, I win. Okay, so that's basically what you do. So very simple stuff. One thing that was interesting in the past case is that it turns out that a lot of the typical targets you would like to attack don't really exist in a platform as a service cloud. And what I mean by that is the tasks often run in address spaces where the keys don't live. In other words, oftentimes in a PaaS cloud, the SSL sessions are terminated prior to the box where the web servers are living. And so some of the things you would typically like to go after with an attack like this aren't there for you to go after. So we had to come up with some other ways of attacking things on a PaaS cloud. And I'll just tell you about one of them, which was a kind of, we're calling a password reset attack here. It's basically a way to hijack accounts on a web server that you're co-resident with. And so it's kind of a neat little trick. What we attacked was something called the Magento e-commerce web framework that offers a password reset capability. The idea is that you go to a web page and you say, I forgot my password. And what happens is when you click that button, it causes a token to be generated and emailed to the account associated, to the email account associated with the web account. When you get that token, you take it and you put it back into the page, and that allows you to reset the password for the web account. And so what we decided to do was to show that we could, in fact, hijack accounts on the website by using this simple attack. The idea was that the attacker would come along, do the password reset on an account that it didn't own, and then what it would do is it would do the flush reload style attack, this attack NFA thing, to watch for when the library calls happened for collecting the entropy that was used to generate the token that would be sent to the real user. And by noticing when those calls happen, we could turn around and call them ourselves, right, we as the attacker, to see what arguments they were giving, what numbers they were giving back to the token generation step. And consequently use that to brute force what was left and figure out what the token is, right? And then take over the account. So the idea is that we would predict the token, we would feed it back to the token verifications part of the web page, reset the password before the user ever got the email. And you would just hijack accounts this way. So how effective does that work? Well, before I show you that, this is a call graph of the password reset process that was used in Magento at the time. And it got its entropy essentially from calls to time, get PID, and get time of day. Mind you, this was not a particularly strong PRNG. It was already kind of weak, or not ideal. But basically, we sort of leveraged its, let's call questionable methods of getting entropy to make them unquestionably, or demonstrate they're unquestionably bad. And there's one other thing you have to get through to make this work, which was how you get over the PID problem. I'll skip that in the interest of time, but basically what you have to do is attack your own account first, brute force the PID, then use that to turn around and attack others. So there's some other trickery you have to do, which I'll skip through here. This is the attack NFA we used. I put this up here not because I expect it to be understandable, but rather just to show you that they're not always entirely trivial. Again, we don't know how to do these automatically, right? We just develop them by hand. And then, right, once you have it, you can do this pretty well. What we found was that after about 2 to the 20 offline computation to brute force that PID after attacking our own account, the attacker gets to narrow down the password reset token after tracking through this flush reload style attack, essentially down to about 4 possible values. So trivial, okay? And so we could essentially arbitrarily hijack accounts on websites this way, just by running next to them. So that was a demonstration that flush reload style attacks were a real problem on, again, this was done on commercial pass clouds. And you might think, well, okay, this flush reload style thing is great, but it does require this page sharing. So isn't just an answer to this to turn off the page sharing? Sure, it means you can't pack your tenants as densely, but look, this is a reasonably serious problem. Maybe you should just fix it that way. But what happened is that right after this, a couple of other groups came along and showed that, look, there's nothing special about the flush reload thing here at all. In fact, what these two papers do is they take that prime probe style of attack that I showed you in the very first attack of this talk, and they apply it to the last level cache. And so the page sharing is not fundamental, okay, and to get these kinds of attacks to work. Rather, the prime probe style attack didn't require page sharing at all. And so if your answer is fix the page sharing problem, that's fine. It just doesn't fix the whole problem, right? You've got another big issue to deal with. That's more or less where the story ends. There have been a couple of works that I'll just mention very briefly that tried something relatively ambitious, which is not just dealing with cache-based side channel attacks, but also broader side channel attacks, larger classes of side channel attacks. One of the ones that we've worked on recently, which I'm not going to tell you much about, is this thing down on the lower right called Nomad. Basically what it does is it tries to remain agnostic to the style of side channel that's being used, but instead just tries to limit side channel exploitation by making sure that two VMs don't sit next to each other very long, essentially playing kind of keep away by migrating stuff all the time. And now the question is, how do you do that intelligently and sort of decide where to migrate what without hurting anything too bad? But if you're interested in sort of more generic defenses, that's one approach, and there's another one up here which I won't have time to tell you about. But if you're interested in this kind of thing, let me know, and I'm happy to talk to you offline. The last thing I thought I would tell you about, which I'll have to be a little bit quick about, but I'll mention briefly, is some work in other kinds of side channels that we've been up to very recently. In particular, so clouds isn't the only place where these side channel problems arise. Another one that's kind of an issue maybe for a lot of us is our own computing devices, our mobile phones. It's very much a multi-tenant environment. As we download apps from the App Store, essentially what you're getting is a whole bunch of tenants running on your smartphones. And now the question is, is it possible for one tenant application to steal information from another tenant application that might be handling some of your sensitive data? So you've downloaded something here, and it's leveraging side channels. In this case, maybe not cache side channels, but in this particular work, we're going to talk about storage side channels, which are a little bit different from timing channels. It's a little bit of a misnomer because it's not really about storage per se. It can be out of things like memory usage or CPU usage or sensor data on the platform that the attacker is monitoring to learn things about what the victim application is doing. And in doing so, might steal some information from that poor tenant. It turns out that smartphones and lots of other, well, at least Android smartphones and other Linux-like systems export a way of gathering data very conveniently like this, called the Proc file system. Been around for a long time. This is a pseudo file system that exports statistics about memory usage, CPU usage, and so forth of different processes on the system, typically for system monitoring and admin kinds of tasks. On a platform like Android, it's used by many apps that you download to sort of monitor your platform for you and do interesting things. If you've used applications like Top and PS on a Linux box, then you know what I'm talking about. Again, if you go look in the App Store for Android, there's lots of other examples of things that use, say, the Proc file system too. And again, the Proc file system gives all these stats out. It doesn't require any permissions on an Android box to allow access to these things. And there's been kind of a cottage industry in the security community showing how these kinds of statistics can be leveraged to learn all kinds of interesting things. I won't go through too many of them, but here I'll take you through one very quickly that was discovered by some folks in 2013, whereby an attacker application that's running next to a browser can monitor the memory usage over time of the browser process, and in doing so classify what web page you're actually going to. And in doing so, maybe learn some stuff about you, like your political interests, your religious beliefs, whatever. And maybe you really didn't expect this particular application. Maybe that's Angry Birds over there, from figuring out that you're a big Trump supporter or something. I don't know, right? So that is the kind of thing we're worried about here. And so the last little project I'll tell you about is some work that we've been trying to do to limit that kind of leakage from storage side channels like the Proc file system. And basically, the solution involves a couple of different pieces, which I'll summarize very briefly to you. One of them is what we call, is called, I should say, deprivate data release. And then there's a secondary step where we have to patch up some invariance that applications might expect. But I'll get to that in a moment. Let me motivate this deprivate data release thing for you. And what it does, it leverages something called, differential privacy. If you've been following the statistical privacy literature, you're familiar with this notion for sure, because it's a very popular notion. At a very high level, it's a strategy by which you protect individuals' data from inferences about it. So if you exist in a database, let's say database D, and this database is being used to serve different kinds of queries, summary queries, like what's the average height of people in this database, or what kinds of diagnoses have they had, and how does that relate to different kinds of features of those individuals. Differential privacy gives you a way of protecting individual users by comparing the outputs of D with the outputs of another database D prime, where, say, one individual is removed from the database. And differential privacy effectively guarantees that the probability that the query algorithm on database D produces any given solution S is very closely related to the probability that the same algorithm on a slightly different database will produce S, that different database being the one that doesn't contain an individual user. And so if that's in fact the case, then clearly you're not leaking very much information by revealing the value S about the individual that is in D but not in D prime, because you're giving the same answer with very similar likelihood in either case, okay? The amount of difference between those two probabilities is characterized by this extra factor here, parameterized by a value epsilon. So as epsilon gets small, increasingly the two databases become indistinguishable. Now, deprivacy is a generalization of this idea that parameterizes it not just by epsilon, but also a distance between the databases. Or more generally, we're going to call them a distance between two objects, x and x prime. Now, in the case of D and D prime, the two databases, you might think of it as a Hamming distance, where the two bit strings they differ by 1 based on whether that user is there or not. In the case of x and x prime, this can be an arbitrary distance metric. And now it's going to be parameterized not only by epsilon, but by the distance between the two objects. And so if both epsilon is small and the distance is small, then these things are going to be relatively indistinguishable. Now, to implement this for the Proc file system, we essentially had to solve 3 problems, right? One is, what is the sensitive data object that we're going to sort of protect here? What's the distance metric, and what's the algorithm that we're going to use to protect it? To cut it for sort of a longer story short, I'm going to just quickly summarize that essentially the object X is, the first thing you would want to do is, say, protect the outputs from the Proc file system. What we instead did is we said, well, there's an error or waste, which are the kernel data structures that are used to generate those outputs. So we sort of did this at the level of the kernel data structures that keep track of this information. Now, what the adversary is doing is it's actually reading a sequence of values over time, right? So rather than just querying it once, it gets to read it over and over and over again. So we have to somehow protect this data, these kernel data structure values, as the adversary reads them over and over and over again, and provide this essentially privacy protection for the values. The distance metric that we chose was leveraged or was based on the style that a lot of these attacks take. The style that they take really looks at looking at a series of values over time, like those data memory size values in the browser case. The attacker was looking at the sizes over time and using that sequence or the differences between subsequent readings to really tell what the victim was browsing. So to, again, sort of quickly summarize what we were doing, this gave rise to a distance metric which looks at the difference between subsequent readings of the two objects, right? So xi and xi minus 1 are two subsequent readings. This is how much the readings change in x. This is how much they change in x prime. And then how much are those differences different, okay? So that kind of, that's what the distance measure is. It turns out that this is more powerful than just looking at the individual attacks that we were addressing or that have been developed in the space. It turns out that this is closely related to L1 distance. And if you take general results about embedding any other distance metric in L1 with low distortion, that there's, in some sense, using this metric as the thing to build your defense on gives you strong assurance about a lot of different metrics that the adversary might be using. But that's a much longer story than I have time for here. The last, I'll skip this. The last sort of piece of the puzzle is what are you going to do? What's the actual algorithm to add noise to the values, right? So that you hide these inferences. For this, we just got to borrow something from somebody else. It turns out the algorithm already existed out there. It was just expressed in a narrower way than what we needed. And so we just had to generalize it and prove that, in fact, this algorithm already did what we wanted it to do. And so this is an algorithm by which you essentially add noise to the results, the query results of the Proc file system, or more specifically to those kernel data structures when they're being queried, to hide the sort of inferences that could be, or prevent the inferences, I should say, that we're concerned about here. The last thing, which I won't touch on, is once you've messed up the values by adding noise to them, there are a lot of applications built over a Proc file system that expect certain things, like maybe that the memory size isn't negative. You know, for example, you're adding noise to these things. You might just break them. So another step, which I won't describe here, is you need to reinforce some sanity on the values you're returning. To do that, we had to extract invariance from these data structures. I'm not going to go into how, but we had to sort of come up with a bunch of invariance about what sane outputs from the Proc file system should look like. And then we had to reestablish them before we return them. Okay. Now, to just show you that this can sort of be done effectively, this is the same website attack, right, conducted on the Alexa top 10 websites. Okay, so again, the attacker's monitoring the data memory sizes of the browser process on, say, your Android phone. And it's trying to distinguish among 10 different web pages that you might be visiting. And basically what this shows is that you decrease epsilon, okay, for these 10 web pages, you can reduce the accuracy of the classifier that the adversary can build from its best of around 90% accuracy down to, say, order 17% ballpark, okay, as you decrease this thing. Now the question is, what does it do to the utility as you do this of, say, the Proc file system, because you're adding noise to the outputs? Well, in the interest of time, I'm not going to show you too much about this, except to say that if you look at the top K rank using, say, data memory size, right, the same feature out of the Proc file system, in an experiment where you have, say, 10 processes with equally spaced data memory sizes, what you end up with is pretty good accuracy, right, for the top 1, 3, 5, and 10 rank, okay, at a security level that would give you, in that website fingerprinting attack, of only 35%. So there's a way to balance, in this case anyway, how secure you make this versus still getting useful statistics out of your Proc file system. I realize that was a very quick summary of the evaluation. I apologize. I just realized I was a little bit behind. Anyway, if you're if you're interested in this stuff, let me know and I can tell you more offline. So that's the story I wanted to tell you with 2 minutes over. Sorry for that. There's a lot of work in this space of side channels. It's a very fast-moving area, and there's a lot to follow. So if there's other pointers I can give you to other work in this space, don't hesitate to ping me. I'm happy to share what I know. So thank you very much for your time. Really appreciate it. Please. Yes.
Very fascinating talk.
Thank you.
Scary. So I wonder if people have looked at rewriting key protocols, the key algorithms, cryptographic algorithms, so that from a resource perspective, they don't reveal anything. So for example, if you take your example, right?
Yes.
If D is 1, you do 4 operations. If D is 0, you do 2 operations. You can always rewrite that.
Absolutely.
So that it looks similar from a caching perspective. Just put in some fake operations in there.
That's right.
People work on alchemy, of course, we do this
Yeah.
for the key algorithms.
Yeah, so it's a great point. In case you didn't hear the question was about, can you build your algorithms so that they're not susceptible? They don't leave a footprint in the cache that's so telling. And the answer is absolutely yes. In fact, modern cryptographic implementations try to address this from both a timing perspective and a cache footprint perspective. The trouble comes in generalizing that idea to everything, right? So in other words, if you don't really know, sure, you can do it for AES, or you can do it for RSA or Elgamal, or your key cryptographic operations. But for other things that you may want to protect, there have been, people have looked at compilers for translating code to not leave any such footprint, but it turns out to be remarkably expensive to do this. I mean, I'm talking factors of 20 plus, at least in the examples I can remember. And so, yes, you can do it. And for cryptographic implementations, it makes sense to do it, I would suggest. If you want to do it more broadly to protect other things that maybe you don't know yet what you should be protecting, it's going to cost you a lot, unfortunately, at least as far as I'm aware.
But those techniques are complementary to anything else you can do, so it might be okay to do it just for key protocols.
Absolutely. Another thing I should have mentioned is, one of the best fixes to this would be to redesign the caching, right? At least for the cache-based side channels that I talked about, so that you don't leak information the same way through the caches. And that's a compelling, I think that's a compelling way of fixing a lot of these problems. The trouble, of course, is that you first have to get the Intels of the world to buy into it. And then once they start shipping, you consider the fact that Amazon and Azure and all this stuff each has 1 million plus machines. So now the question is, how many years before the fix gets deployed, right? And so in some sense, I think there's some merit in looking at other solutions to the problem as well, as you're suggesting with algorithmic fixes. That's right. And in fact, in some sense, the past guys were smart in doing that for other reasons. That was exactly the reason we couldn't go after the keys in the platform as a service case, is because a lot of these clouds don't even have them there. And they, of course, do it for a different reason, but it turned out to be very fortuitous. Yes?
Sometimes, I mean, of course, a lot of this is whack-a-mole at the end of the day, trying to identify sources of leakage. But I wonder what you're thinking on
So, it certainly slows things down for the attacker. And a number of the defenses, some of which I really didn't talk about here, have elements of that in them. In some cases, I mean, it's very hard to sort of characterize all such solutions sort of under one umbrella, but in a lot of these cases, statistics eventually will overcome the randomization. In others, maybe you can make a compelling argument that it won't. But I mean, I should point out that, for example, that the side channel defense, the last side channel defense I described, where we're adding noise to the ProcFS outputs, is an example of this sort of randomizing the values. But it's a great case where in order to keep the statistics from eventually winning, the amount of noise you're adding per query is growing, right? And so the values are getting noisier and noisier and noisier. And so either you eventually have to reset this by restarting the process or something like that, or maybe divvy it up per user that's querying or per tenant that's querying. So that if I make a bunch of queries to the Proc office, I don't mess up all your queries, right? Something like this. But yeah, there's a lot of interesting interplay in the various issues associated with randomizing. Yeah. Yes.
So are there side channel attacks on side channel attacks? How detectable are these attacks? Could they just be detected and then,
Yeah, so great question. The first attack I described to you was sufficiently detectable that we were uncomfortable. It was downright intrusive, right? In other words, we were uncomfortable running it on a public cloud because we thought it was just too intrusive. The one we did run on the public cloud was sufficiently unintrusive that, in fact, we had a hard time detecting it. Now, that's not to say, I mean, we didn't set out to write a research paper saying that these are undetectable, okay? So it's not, I'm not saying that I don't mean to stand up here and go, they're not detectable, right? But they were sufficiently under the radar that I think it might be hard. That's a great thing for someone to improve on, right? So.
do you have more questions?
Well, again, I really appreciate your time. Thank you very much.